welcome to the first video in a series of videos where I'm going to discuss recursion and the benefits of recursion. First off, there's two types of programming that you should be made aware of. There's what's called iterative programming, which is what you've been doing all along, from first semester to the first half of this course. An iterative program is one that calculates its solution based on loops. Now, for instance, the factorial, you'll remember what a factorial is. A factorial, say, this is the symbol for factorial, the exclamation point. The factorial of 5 factorial is equal to 5 times 4 times 3 times 2 times 1. That's the calculation of the factorial. Very important in mathematics. You could certainly do that program, the factorial, using a loop. Okay, you start off with your answer that you're going to return. We start off with 1, and then we go ahead and say, well, have I go from 1 to 5, so that'll be 1, 2, 3, 4, 5, and take that I and multiply it by the answer. Answer is equal to answer times I, so times 1, times 2, times 3, and you accumulate all the multiplications and you return the answer. Well, certainly you can do that problem iteratively. In fact, I would do that problem iteratively, because it can't get any easier than what I just showed you between lines 8 and 13. But there's also another way to do that, and that is with recursion. And a recursive program generally doesn't mean you. This is a hard and fast rule. Generally, a recursive program doesn't use loops, but that's not always the case. Okay, sometimes you need to have a loop in your recursive program to simplify your programming. But most of the time, a recursive program doesn't use a loop. And if you take a look at lines 16 through 22, this factorial program, which in fact works, okay, you have to take my word for it, does return the same value as the iterative program, but it looks radically different. Look at the two values, the two methods. They look totally different, but they produce the same answer. Now, what makes a recursive program recursive is the fact that in order to calculate the factorial, you need to call that factorial program again with a different number. You see that? So you're used to having basically, when you call your method, you used to have your methods call another method, and then call another method, a different method. Okay, you can go 5 to 6 levels deep in your methods, but you always know the way it works. Once you go 6 levels deep on that 6th method, once it returns, it goes back to the 5th, maybe passing back a value. The 5th goes back to the 4th, and so on. This is the same whether you call yourself or you call a different method, it works the same. It's just that people get all nervous about, well, geez, you're calling yourself. Why does that work? Well, let's give you an example of why this works. Say I would like to calculate the factorial of 4. So you know 4 times 3 times 2 times 1 will end up being 24. But how does this calculate recursively? Well, according to this definition, line 18 is called the base case. The base case is where the factorial doesn't do any calculation whatsoever. Okay, and it turns out if the number that you pass as the parameter is equal to 0, basically factorial of 0, then the factorial of 0 is 1. That's the accepted value of the factorial of 0. If it's not 1, like in this case the number is 4, well, what happens is the factorial of 4 is equal to 4 times the factorial of 3. So what you've got to believe when you think recursively is that you're trying to get, with each call to factorial or each call to the recursive function, the parameter 3 gets closer and closer to the base case. Like in this case, the factorial of 3, well, geez, it's 4 times the factorial of 3, even that's too complicated. So what the system does is it calls factorial of 3, and in this case, number is equal to 3. Now the number that was in the first invocation of factorial is different from this number. Okay, these values that are these parameters, any local variables, every time you call a function, those parameters and those local variables, I don't see any local variables here, but parameters and local variables are stored in what are called stack frames. So the first time you call factorial of 4, you have a stack frame that contains number equal to 4. Okay, then factorial 3 needs to be calculated. Okay, that 4 doesn't go away. It's stored in a stack. Factorial of 3, that's 2. See, 3 is equal to 0 false. I can't do that. It doesn't go to the base case. So 3 times the factorial of 2. Okay, so that 3 is stored in a stack frame. Factorial of 2 is too complicated. 2 times factorial of 1. Factorial of 1 is too complicated. 1 times the factorial of 0. So if 1 is passed to the factorial, numbers equal to 0 is false. So in order to calculate this, the factorial of 1 happens to be 1 times the factorial of 0. Now it has to go one more level, factorial of 0. 0 is equal to 0, return 1. So the value of factorial of 0 gets returned as the value of 1. That 1 comes back here. 1 times this value, this stack framed 1 is 1 times 1 is 1, so factorial of 1 is 1. 1 gets returned here. 2 times 1 is 2 for the value of factorial of 2. And we're going back up to the next stack frame. 2 times 3 is 6. Factorial of 3 is 6. We come back up here. Factorial of 3 is 6 times 4, and we're done. This is generally each level. Each time you invoke a recursive function, you're trying to get closer and closer to this base case. And if you don't get to that base case, if you move away from the base case, you could never return a value back. And what you have is called infinite recursion, and you need to prevent that from happening. So if by accident I said something like this, plus 1, see, if I pass it 4, then you're calling factorial of 5. You're never going to get number 1. So let's go ahead and show you what happens if that is the case. I have my main program here somewhere toward the bottom here. Here's my main program, factorial. Let's go over here. Okay, factorial of 4. Look at this. We've loaded up the memory with all those stack frames, and that's a problem. Okay, so what happens now is we go back and fix it. Where do we go? Fix it right there. That plus should be a minus, and I think it should work right now. There's your number 24, and that's because it's calling this function. Now, would I do it this way? Nah. This is just more complicated than it needs to be. In fact, it's probably wasting more memory too, because every time you call a factorial, you have to create another stack frame to hold the local variables. Where that's not true here. You just have one stack frame, and that number variable, okay, gets passed. You have a local variable answer, and that local variable gets changed, okay, in one stack frame. So I would say this is just an example of what you need to do to explain factorial. Another way to do this is, well, I'm going to hold up on the tail on this solution until we get down to understanding recursion a little bit more. I'll do the tail recursion in another video. But the Fibonacci sequence. First off, what is Fibonacci sequence? Well, we start off with 0 and 1. That starts off the sequence. And then to get the next number, you have to add the previous 2. So this number here is 1 plus 0, which is 1. Another one is, this value is 2, because 1 plus 1 is 2. Next value is 3, 5. That's the Fibonacci sequence. And now 13, and etc., etc., etc. Okay, this is the 0th. The first one is the 0th. Let me go over here and put the index, the end value. 0, 1, 2, 3, 4, 5, 6, 7. so if I wanted the 7th Fibonacci number, okay, that we need to go back and calculate the 5th and the 6th Fibonacci numbers, get those values, add them together. Okay, how do you do that? Well, you could certainly do this iteratively, but what I'm going to do is show you how you actually, it's probably easier to do it recursively, actually. All right, now Fibonacci 2 is the way is what I'm going to describe first. Okay, it's what's in the textbook. It's also your second classic example of Fibonacci. So Fibonacci 2 as opposed to Fib. We'll talk about Fib later, but Fibonacci 2. So if I pass it 7, see 7 should return 13. So n is 7. Okay, we worry about the base case first. The base case is if n is 0 or n is 1, there's no calculation involved. Those are givens. Those are a give me. Okay, if n is 0 or 1, then you just return the value 0 or 1, depending upon what you have here. But if I pass it to number 7, in order to calculate the Fibonacci of 7, what I need to do is call the Fibonacci of 6, n minus 1 is 6. And what you do when you think recursively is think optimistically that it works. If I were to pass in 6, whatever, the 6th Fibonacci would be 8. Okay, let's assume, don't worry about all the sub-micro calculations, that if I pass it 6, it's going to return 8. All right, so this 8 gets returned and stored, okay, internally to by Java, because it's not going to throw that 8 away, because it needs that 8 in order to be added to this next calculation, Fibonacci of 5. Remember, n is 7 at this level. 7 minus 2 is 5. Fibonacci of 5, let's hope it returns 5. So that 5 and that 8 gets added together, and we return to 13. Let's see if that's the case. Let's see if that is the case. So we go back to our main method to invoke this thing. Okay, we'll do this as Fibonacci, fib of 2, we'll pass it 7, that's the 7th Fibonacci number. We return this, let's see if we get 30, you get the 13, perfect. Now, you could certainly do this iteratively, all right, and I'll challenge you to do it iteratively, but really, let's think about doing this properly, and that is, well, I wouldn't say properly. I would say we have to start thinking recursively. And the key to doing this is worry about a base case. Okay, the base cases require no calculations whatsoever. You just return the value, 0 or 1. Okay, now if I pass it anything other than 0 or 1, you need to calculate Fibonacci based on the value of this parameter. You assume that what comes back correctly, okay, and then you do the same assumption here, that comes back correctly, so those two numbers have to be added together in order to get the proper value. So, and mathematically, it makes sense. If I were to pass it fib of 2, mathematically, according to the definition of Fibonacci, it follows nicely that the Fibonacci of 2 is equal to the Fibonacci of 6 plus the Fibonacci of 5. Okay. Now, don't worry about Don't worry about all the sub-micro methods that get called. You just say eventually it's going to come back. This value gets returned correctly. This value gets returned correctly, and so if those two values come back correctly, then this value comes back correctly. Okay, so we'll stop here. This is your introduction to recursion using the classic examples of Factorial and Fibonacci, and then we'll worry about a bunch of other examples later. Okay, take care. See you in the next video.